All right, so we are live now and we will begin. Since this is going to be a very long session, so what I will do is the first 50 minutes we will discuss about Dirac delta, and you have to see why I'm not calling it as Dirac delta function. Okay, so obviously, being a mathematics student, I can't call it as a function, and I will tell you why I'm not calling it as a function. Okay, so we will discuss about Dirac delta, and we'll solve a couple of problems related to the Dirac delta. Okay, so we will do that in the first 50 minutes and then we'll take 10 minutes break. And the last 50 minutes, either we will do practice assignment problems, or if you have any doubts in till week 4. So, right from week 1 to week 4, if you have any doubts, we can discuss that, or else we can end the session early today. Okay, and on Saturday, we will do a short demo on MATLAB, and that is only you join only if you don't know the basics of MATLAB. Okay, so we will start from very basic thing. How do you define a variable? How do you define an array? Okay, so we will just start from very basic. If you know, then you can skip that particular session. Okay, so yeah, so Saturday session will be the basics of MATLAB, and today we will conclude week 4 until week 4. And next week we will be doing week 5, not the revision sessions. Okay, so I hope most of you know the deadlines and everything. So our week 5 deadline is before than your quiz 1. So we'll do week 5, then revision sessions, and then you will attend quiz 1. And after that, we will move to week 6 and so on and so forth. Okay, is my audio clear to everyone? All right. Okay, let's begin. Let me understand from you. When we say Dirac delta function, how do you define a Dirac delta function? Anyone? So what do you understand when you see Dirac delta? Okay, pure silence. Okay, so let me ask you this question then. So how many of you think Dirac delta is this? Okay. Uh, okay, I will put a poll now in the session itself. Okay, so you have to click on the activities and there will be a drop down, and within that there will be polls, and you just have to vote. So I'll give you 2 3 options, or for this particular question, yes or no. So if you feel yes, this is the definition of Dirac delta, just click yes. If you feel this is not, then click no. Okay. So do you think, or is this the definition Dirac delta function? Okay. So yes and no. Yeah. So I have created a poll. If you are unable to find it in the meet, click on the activities button. So there will be shapes, triangle, square, and circle all together. So click on that, and there will be some two, three different subsections. Within that, you will see poles. Click on that pole. You can cast your vote there. And why am I doing this is because this will count as your attendance. Okay, so I will do some 3, 4 polls randomly throughout the session. And at least the standalone student should answer all the 4 polls. Okay, so you may not be correct, but at least I will get to know that you are in the session. So you didn't run away from just joining in the mobile and kept it in one room, and you just went to play or watch movies. Okay, so only 6 of you have attempted so far, 7, and I see there are 25 students. And I will end it in 1 or 2 minutes. Okay, so it's not that it will be there till end. So the first poll will end in my maybe say 8:13. I will end the poll. Okay, so try to attempt the poll by 8:13. Okay, so the thing is actually Dirac delta mathematically uh, we can't accept that as a function because Dirac delta is not actually a function. It is called a functional or a distribution. Okay, so in that way you should define it. So this should not be called as a function because when you call it as a function, function has certain properties, right? Like it has every input, there should be an output properly defined. Well defined functions are given input, it will output you a value. And it should also satisfy when you multiply one function with another function. So you can do product of functions. You can add two functions. When it comes to delta, this thing, delta of t. So, okay, anyway, so Dirac delta is denoted like this, right? So delta t represents Dirac delta. Now, what do you mean by Dirac delta multiplied with Dirac delta? Does it make any sense? So, what is Dirac delta multiplied by Dirac delta or Dirac delta square? So, if it is function, you should be able to tell something about delta square, right? So, we can't say anything about delta square of t. It doesn't mean anything. But when it comes to engineers, physicists, they are okay with delta t. They call it as function and they don't worry about the technical proofs or proving delta t is a function. They don't care. They will just use it delta t. It is helping them to, it can be thought of as a sudden change in current or voltage, sudden shift. And they will use it in many other places wherever is necessary. And delta t is actually used in Laplace transforms. Okay, so Fourier transforms. So we'll use this Dirac delta in our course also. So it will frequently come. But so that is what. So physicists and engineers, they don't worry about the classiness of the functions. They just simply think this. So delta t is 0 at all other values except at t is equals to 0. T is equals to 0, it will have an infinite peak. And the graph also, if you see the graph of Dirac delta, it will be like this, right? So or like this, right? If it is t, this is delta t. And what does this actually represent is, they'll just simply say, if t is not equals to 0, the function delta t is 0. And this peak will, there is no ending point here. So it's like a line, it goes till infinite. But the only catch is, if you compute the area under the curve, it should be equals to 1. So that's all they want. Okay. But when it comes to how do you define or how do you argue this as a function, then it loses. You can't do simple operations of functions on this Dirac, right? So that's where this conflict has arisen. But luckily, Squares, so mathematician Squares has come up with Squares distribution theory, where he actually provided a mathematical way of defining this Dirac delta. That is actually defined like this. So the correct definition of Dirac delta is as follows. So whenever somebody asks you, if you want to satisfy both mathematicians as well as engineers, you give them this particular expression as the definition of delta. So when you take some function, okay, any continuous function at t is equals to 0, and multiply it with delta t dt, you will get f of 0. And provided that this f of 0, f of x or f of t is continuous at t is equals to 0. Okay. So this is the actual definition, and this is mathematically also correct. Okay. Whereas this definition, it is okay if you are an electrical engineer or physicist, but it is not okay if you are mathematically inclined. Okay. So any arguments, any thoughts on this? Anyone? So this is correct definition. And this is also called sampling property. Yeah. Okay, so let me hear from you guys. What do you think about Dirac delta? Should we call that as a function or not? Oh my god. So you don't want to get into trouble by answering. Okay, fine. Okay, so then if you understood Dirac delta, answer this. What is delta of 0? Come on, if you have understood this, then you should be able to answer this.
So is it 1?
Okay, so I'll give you options. Again, I will create a poll. Yeah, option A, infinite. Option B, 1. Option C, 0. And option D, undefined. Okay. So since you guys are not answering, let me just put this as a poll again. So delta of 0 is equals to infinite, 0, 1, undefined. Yeah. So I have created poll 2 for standalone students. I already told this is important. Even though you know the answer or not. So yeah. Pratibha, can you mute, please? Yeah. So I have created a poll in the Gmeet. All the standalone students should answer it. If you know the answer, click the answer that you think. If you don't know the answer, at least click or guess the answer. Okay. So the right answer is infinite, but I don't even agree with infinite. You can argue if you say delta of 0 will actually go towards infinite, but it's not infinite. Okay. So it is a very large number, but it's not infinite. Once I say it is infinite, then the area under the curve will become infinite. Right. So I need to satisfy this thing. So minus infinite to infinite, delta of t dt should give me 1. When I say delta of 0 is infinite, so the area under the curve will not give me infinite. So infinite wouldn't be the right answer. What if I say delta 0 is 1? Will it be correct? That is also wrong. Right? Why? Easy. The way in which we define. So you see this. And yeah. So again, let's come back. This delta 0 is equals to 1 also doesn't make sense because delta delta is basically, again, if you go back, delta is not a function. First of all, if delta 0 becomes 1, then you have values for all the thing, right? Like it is like a it is like this. So the height is 1 at 0 and all others are zeros. So it's like it is equivalent of saying that your delta of t, what you're saying is it will be 1 when t is equals to 0. It is 0 when t not equals to 0. This is not the actual definition of Dirac delta. This is, let me see, anyone knows this? This falls into chronicle delta, which is in discrete case. Okay. So if you have this kind of thing, then the integral of this will become 0. Right? So minus infinite to 0 minus delta t dt plus, so you can write this integral as integral 0 minus to 0 plus delta t dt plus 0 plus to infinite delta t dt. Now this is anyway 0, this is also 0, and delta t here, as we are saying that it is only at one point and it is equals to 1, then here it is like integration of 1 dt, and this is almost 0 and 0, which is like, if you see the area under the curve, there is no area itself, so area under the curve becomes 0. So this is also not correct. Delta 0 0, not a possibility. Delta 0 undefined, you can say. So it is not properly defined, like it is going towards infinite, but you don't know what the value is. It is not even infinite also. Okay. But to our textbooks back again, like what we define is delta of 0 is infinite. So in our signals and systems at least, and we'll ignore math and we'll just move ahead. Okay. So the next thing is, again, I have brought this up, right? So integral minus infinite to plus infinite delta t dt is equals to 1. So how do I get this from my actual definition? As I said, my actual definition is minus infinite to infinite. I have some f of t, delta t dt, f of 0, right? So if my f of t, if you put f of t is equals to 1 for all t, you consider that kind of function. So this function is continuous at t is equals to 0, right? It's just a horizontal line. So if you consider that, then your f of t becomes 1. Then this will simply become minus infinite to plus infinite 1 times delta t dt is equals to f of 0 is also 1, because f of t is 1 for all t. So therefore at t is equals to 0 also it will be 1. So you can get this area under the curve of delta t thing is equals to 1 from the definition itself. So now this makes sense, little sense, right? So this particular thing, if you define delta t such that when you multiply it to some function and you integrate from minus infinite to plus infinite, if it gives you the function value at 0, such kind of function, such kind of function is called as Dirac delta, right? And is this the only function that satisfies this condition? Let's say this condition is 1. So we'll use this condition 1 very frequently in this session. And again, so this session, the major agenda or major aim that I came up is, since you're all going to move ahead and one day you will be using this delta a lot. So if you are not worried about the theory behind delta, then this particular session may not help you. This particular session's main agenda is to give you some understanding on how this Dirac delta has came into the picture. Okay, and the theory behind the Dirac delta and the proper way of defining Dirac delta. Okay, so that is my aim. Okay, so back to what I'm saying. So a function, so let's say phi of t is Dirac delta function if there exists a continuous function continuous function at t is equals to 0, such that minus infinite to infinite there exists a continuous function f of t at t is equal, so continuous at t is equal to 0 is sufficient. If you have continuous function, then that is also okay. So integral minus infinite to plus infinite f of t, this phi t dt, if you integrate and if you are getting f of 0, then we say that phi t is called the Dirac delta function. And there are many other forms also. So this is the proper way of defining Dirac delta. Okay. So Dirac delta is actually derivative of u of t, right? So that you have studied from the lectures. But in order to see this d, like u prime of t, right? So u prime of t or dut by dt, whether this is actually Dirac delta, what condition you should check is when you multiply this function or this expression with f of t, if it is giving you f of 0, then dut by dt can be referred to as delta t, right? So it is also one form of Dirac delta. Okay, so that can be proven using fundamental theorem of calculus. So if I consider minus infinite to plus infinite some function f of t dut by dt. Okay, so now since you guys have studied math 1, you have two functions in the inside the integral. What should we use? Integration by parts. How many of you remember this?
Yes, sir. By
Yeah.
part.
Yeah, integration by parts. So use that integration by parts, you will get f of t integral of this dut by dt, which will give you u of
Like
t,
function.
and infinite minus integral of, you take the derivative of f of t, which will be f prime of t times the integral of dut by dt, which will be u of t, dt. Correct? Right. So this is from minus infinite to plus infinite. Now you see this f of t into u of t. If I multiply the if I substitute the limits, f of infinite times u of infinite. What is u of infinite? U is unit step function. Okay, is my are my questions are too easy to answer, or is it too difficult to answer, or is this going way above your head, or I'm not able to understand. So,
One, sir.
so u infinity is 1. What is u minus infinite?
It is 0.
Okay. So now what happens to this? So this will become 0. This will become 1. So this will simply be f of infinite. Right? So this term will vanish. There is, because u minus infinite is 0. So 0 times f of minus infinite will be 0. So you'll have f of infinite from here. Now you see this. It is integral from minus infinite to plus infinite, but you have f prime of t into u of t. And u of t is defined from, or u of t is non-zero when t is greater than 0. Right? So that integral can be written as, instead of minus, so minus infinite to 0, it will be 0. U of t is 0. So you don't have to consider that. It is enough to consider 0 to infinite f prime of t dt. Right? Because 0 to infinite u of t is 1. Now integral f prime of t dt, if I use fundamental theorem of calculus, so f prime of t, if I integrate, I will get f of t, and the limits are infinite and 0. Okay, so if I substitute the limits, I'll have f infinite minus, this is like f infinite minus f of 0. This and this will get cancelled out. Minus of minus will give us f of 0. So now what we proved is, we took a continuous function which is continuous at t is equals to 0 and multiplied it with dut by dt, and we got f of 0, which implies that dut dt is an Dirac delta function, which is delta t. Okay. Okay. So if you are not surprised yet, maybe the next slide you will get more surprised. Okay. So far what I said is the
Sir,
proper way of, yes,
sir, this f of t is any arbitrary function or
f
is
of t
any
is,
arbitrary signal, or what is this f of t?
sorry Pratibha, I think your voice is breaking. Can you repeat what you said?
Sir, I'm saying that this f of t is any arbitrary function.
So f of t is any arbitrary function, but the only condition on f of t
That
is,
you multiply by this d by dt.
okay. Yeah, so this f of t is any arbitrary function. The only condition on f of t is it should be continuous at t is equals to 0. That's it. There is no other condition on f of t. Okay, f of t is a very nice function which should be continuous at t is equals to 0. And it is arbitrary, any function. It can be exponential, it can be polynomial, it can be some discrete outside but continuous near 0. That is also okay. Okay. So that is the definition. If there exists a continuous function f of t, that's it. Okay. So I hope this is little bit clear. And yeah, so coming to the surprising part, so far you would have studied delta of t is actually dut by dt. And when I integrate minus infinite to t, delta of t dt, right, I will get back u of t. Correct. So this also professor has discussed in the lectures. But yeah, and also he has shown you that graphically delta t is just a very vertical, small vertical rectangle, right? So where this is epsilon, that means this is minus epsilon by 2, this is epsilon by 2, and the height is 1 by epsilon, right? So if you define this as some delta epsilon of t, and this is t. Now as epsilon tends to 0, so limit epsilon tends to 0, this delta epsilon of t will be your delta of t, right? So that is also one way of defining your delta of t. But I mean, why it need to be a rectangle? Why can't this? Okay, consider this minus minus epsilon, and the height of this rectangle is 1 by epsilon. Okay, so you maintain the height of the rectangle to be 1 by epsilon, and you maintain the interval that this is non-zero as 2 epsilon. So now it is like half into base into height, which will give me the area 1. Right, let me define this as define this function as some delta tri okay delta epsilon prime of t. Okay, so this triangle delta epsilon prime of t. Even if you tend this epsilon prime delta epsilon prime to 0, this is limit epsilon prime going to 0, delta epsilon prime of t. What do you think this also will look like? How does this look? Any guesses? So this green thing, this triangle, the two sides of the triangle are coming closer and closer to each other towards 0. Okay. And the height of the triangle is slowly going to infinite, because 1 by epsilon prime, where epsilon prime is 0, going towards 0. So 1 by 0 will go to infinite. Again, this is kind of looking like delta of t. Yes? No? No comments? Anyone? No? Is it too confusing now? Okay, so this won't go to delta of t, is it? How can the rectangular pulse is going to delta of t, and why not the triangle one?
Because sir,
So
when
these
we
are the things you should.
calculate the area of circle,
Huh. So area of the green one will also
we calculate
be 1, right? It will also be 1, right? So if I integrate minus infinite to plus infinite, delta epsilon prime of t dt, this will give me 1. And as epsilon prime tends to 0, I can say delta epsilon prime of t is 0 for t not equals to 0. So that is why I said, so if you define your Dirac delta like this, then there is no proper functional way you can represent this particular Dirac delta. Okay, so these are some thoughts I am leaving it to you guys. So if you are interested to learn more about Dirac delta, so you can actually visit uh, Oppenheimer. I suggest Oppenheimer. So that is where I got these all these thoughts. And yeah, so if you are interested, again, anyway, we have Google, and nowadays AI is also far advanced. So you can have a chat with one of the AIs that you like. Okay, so whatever you are thinking, so far, Dirac delta is so easy. It's not that easy to understand. Okay, so definitely this is not true. What is this? Yeah, delta of 0 is 1, and at all other places it is 0. So that is not the Dirac delta. Okay, and finally, before going to the problems, another way. So not only this triangular pulse, so you take this standard normal Gaussian, right, where the standard deviation is 1. You take that as sigma and tend that sigma to 0. Something like you take your function as mm, so g of t as 1 by 2 delta into e power minus t square by delta. Okay, so even if you consider this, and if you tend delta, so if you tend delta to 0, g delta of t will look like delta of t. Okay, again, how do you check this? Put this, take this and substitute here. In place of delta t, place it here and multiply it with some continuous function f of t and do some manipulations. You will finally get f of 0. Okay, so yeah, so after 45 minutes of thoughts on delta of t, Dirac delta, it is up to you now to decide whether you want to be an engineer or a mathematician. Okay, so if you are too confused, then just leave whatever we discussed so far. Okay, so whatever there in the lectures, you just go ahead with that. We'll solve a couple of problems now related to Dirac delta, and there you will encounter these things. Okay, so if you are clear on these parts, then Dirac delta integrating, if you multiply something inside, everything will follow. Everything makes sense for you. Okay, so before we move to problems, we'll just write down some properties that we know. We are going to use those properties in the problems. Okay, first one, when I integrate from minus infinite to plus infinite, delta of t dt gives me 1. And the second one, when I integrate minus infinite to plus infinite and take the scaled impulse, this will give me 1 by mod a. So now when you understand this delta of t carefully, then it is very easy to get this particular result also. So I'm not proving it, but you can try it out. Third one, minus infinite to plus infinite. This is the actual definition that I have discussed. If you have any function f of t, delta t dt, this will give you f of 0. And the fourth one, integral minus infinite to plus infinite, f of t delta t minus t naught dt will give you f of t naught, function value at t. Okay. So yeah, I think these are the important properties of Dirac delta that are helpful for us to solve problems. Okay. And also, so this is the graphical representation of delta of t. Okay. So we'll just put like this and we'll just write this as 1. What does it mean is area under the curve is 1. Okay, so this is delta of t and this is t. Okay. If I just if I shift this delta of t by some 2 units to the right, then this is graphically represented like this, and you will put 1 here. And this thing is delta of t minus 2. This is 2. Okay. And delta of t is an even signal. So what does it imply? Delta of t is delta of minus t. So that you can see it easily here. So this is symmetric around y is equals to 0, x is equals to 0 line. So therefore delta of t is an even signal. Okay. So this is shifting. What happens if I scale? So if I scale, so how does the signal delta 2t look? So you'll have yeah, anyone would like to answer? How does delta 2t look? It will be like an impulse. What would you write here? 0.5 or 2? Okay. So let me put my third pole then. Yeah, so delta 2t. Mm, delta 2t peak value. I'll say peak value. Peak value is, will it be 0.5 or yeah. So I have created the third pole, pole POLL. You can just answer it in the chat using that activities button. Click on that activities button and you will see polls. Click on the polls and you can choose an option there. Okay. So here, as I said, this value which we are representing actually denotes the area under that curve. Okay, it's not a straight line going. Okay, so always think of it like there is some width, some width. Okay, so that is why I'm drawing it little bold. Okay, so there is some area being captured within this line. Okay, and this value actually represents the area under the curve. So delta 2t, if we are scaling it in the time signal, it will shrink, but the amplitude will not change. So if the time signal gets shrinked, our area will reduce, right? So think of it as triangle or rectangle, whatever it is. If you're not changing the height, Okay, if you are not changing the heights, but you are changing your base, so you are shrinking your base. So therefore, the area will reduce. So if you are scaling by factor greater than 1, your area will reduce. If you are scaling by a factor less than 1, your area will increase. Here we are scaling it by a factor which is greater than 1. So our base length will reduce. Also our height is the same. And the base is reduced by 2 times. So the area will be reduced by 2 times. So initially we have 1. Now it will be reduced to half. Right? So therefore this will be half. Okay, so now shifting and scaling is done. Now you should tell me, how does or plot delta 2t minus 3. Okay. So if you can plot delta 2t minus 3, then I think the later problems will be easier for you to understand. So scaling and shifting done at the same time. So if you are done plotting, just raise your hands. I just wanted to see how many of you have done. Okay, so 3 of you have already drawn the plot. Good. So try it out, and those who have done plotting, you can take a break. So come back by 9:05. Okay. But those who are solving, please do solve. I didn't ask any difficult question. And since you guys are feeling Dirac delta is so easy, you should be able to plot this. Okay. And those who have plotted, you can just raise your hands and you can take a break. Okay, so I see only 10 people raised your hands. So what happened to the other people? Are you not able to draw this, or you're not able to raise your hand? See, I'm not asking to raise your hand. You just have to click in the Gmeet, right? So if you drew the plot, just raise your hand. That's it. All right. So you guys can take a short break. So come back by 9:05. 9:05 we'll start solving a few more problems, and we'll also solve practice assignment questions. All right. So let's resume. You guys can lower your hands. Okay. All right. So the plot of delta 2t minus 3 will have the impulse at which point?
3.
Anyone? At? Yeah, tell. See,
3, sir.
even though it is wrong, it's fine. Okay, use
3 by 2.
money. Okay, so Okay. So I have plotted an orange curve, orange impulse, blue, black, and green. So which one do you think this delta 2t minus 3 is? Come on, you can guess.
Blue.
Okay, so blue,
Yellow.
yellow,
Green.
green,
Green.
green. Okay, so I see most of you are saying green. Any black? Okay, so I didn't plot right. So this is 3 by 2 and this is 3. Okay, so most of you are saying green, green, blue. Okay, all of you will agree that black one is not true. Pretty evident, right? So this we can ignore. Why not yellow? Okay, so let me answer. So we are actually doing scaling as well as shifting. When it comes to delta functions or Dirac delta, especially, so what is the best way to look at is you look this function as like this. If it is scaled, you pull out the scaling factor and you write this as like this. So now if you observe clearly, so whatever delta of something inside, right? So this, if the inside part is 0, that's where you will have impulse, right? So that's how we have learned delta, right? So if this, when will this be 0 or when will this be 0? At t is equals to
3/2.
3 by 2. So t is equals to what for 2t minus 3 being 0? So you can just substitute 2t minus 3 is equals to 0. Then you will get t is equals to 3 by 2. So that implies that you will have an impulse around 3 by 2. So this is also wrong. Okay, so the black one is wrong, green one is wrong. So the only possible things are yellow or blue. Why is it blue? Why not yellow?
Because we are scaling it, right?
Correct. Correct. So you are scaling, then there is a scaling factor actually. So you are scaling by a factor of 2 and you have an impulse at 3 by 2. So that's how you should look at. So this is the scaling factor, and this is where your impulse will be. So t minus 3 by 2, when will that be 0? When t is 3 by 2. So at 3 by 2, you will have an impulse, and that impulse is actually scaled by a factor of 2. So therefore, the correct plot for this particular expression is blue curve. Okay, so any doubt here? So if you don't understand this, then the next problems will be much more difficult. I want at least 50-60% of the people should get this. Why blue is correct? Why not the other three curves? And trust me, your quiz options will be going to be like this. Okay, so whatever ABCD I have given, those will be your ABCD values, ABCD options. Okay, and if you don't have clarity on Dirac delta and the scaling, when you do scaling and when you do shifting and when you do together, how does the plot of the impulse will look? Okay, so this should be very, very clear. Now, learning this, we will solve some analytical problems without graph. Okay, using the properties. Okay, so if I have to, so this is the first problem. If I want to find the value of integral minus infinite to infinite x square delta x dx, what will this be? So use the properties that we have discussed.
Zero.
Okay. Okay, 0. Correct. Why is it 0?
By the properties we get f of 0, x square, f of 0
Correct.
is 0 square, which is 0.
Correct. So you see now x square is your f of x. Right. So f of x is getting multiplied to our Dirac delta and we are integrating it from minus infinite to plus infinite. We know from the properties that this will be equals to f of 0. So this is your f of x and this will be this will be equals to f of 0. So f of 0 is 0 square, which will give you 0. Slightly easier, right? Now, the same x square, but you are multiplying with delta x minus 2 dx. Or let me give x plus 2. What will this be?
4.
4.
4. Why?
Delta x of minus 2 minus t minus t naught, and then when we integrate, it will give me like f of t naught. So that's why.
Correct. So you write this as delta of x minus of minus 2. And again from the properties that we know, integral minus infinite to plus infinite, if you have f of x multiplied with delta x minus some x naught dx, this is f of x naught, right? It is sampled. So you are sampling at x is equals to x naught, right? You are not considering the whole function. You are taking one sample of the function at x is equals to x naught. So that is why this is called sampling property, right? So the same thing we do here. Here x naught will be minus 2. Therefore, you will have minus 2 whole square, which is 4. So this is also slightly okay. Now, minus infinite to plus infinite, sine pi t into delta of 2t dt. Manisha, can you unmute and mute again? I'm getting slight disturbance. Yeah, thanks. Okay, so Ashish San says it is 1. Okay. Any other answers? So from here, the problems will get slightly trickier, and slowly we will end with one complicated problem. Not too much complicated if you understand Dirac delta, but it will be complicated if you don't understand it. Hmm. So are people doing this, or you're just waiting for me to answer, or what's happening? Is all it and sitting silent? Okay, 0. Yeah. So this is what I want. Conflict between 1 and 0. Okay, how many of you think this is 1? Okay, not think. How many of you guess that this could be 1? 1. Yeah, yeah, please raise your hands. So now, how many of you think this could be 1? Or guess this could be 1? How many of you guess this is 0? Can I see some hand raises? How many of you think or guess that this will be 0? No one? Okay. 2, 3. Oh my god. 6. All right. Then let's solve. So these kind of problems, at least me, since I am not very favorite to Dirac delta. So what I do is I will use my math knowledge here. So I have delta 2t, which is scaled version of the impulse. So what I do is I do a substitution. Substitute some p, or p is equals to 2t. So when p is 2t, my dp will be 2 dt, right? And t will be p by 2, right? So I am just replacing 2t by p and rewrite the same thing. So the integral limits will be same because it is minus infinite to plus infinite. Sin pi, instead of t, I'll write p by 2 into delta. 2t is p, and dt is, again from here, dt will be half dp. So half dp. Now this is, if I simplify, this will be half times integral minus infinite to plus infinite sin pi p by 2 into delta p dp. Right, so this will be half. Now you have a very standard way. some function is getting multiplied to delta p, right? So it's just a variable p or t or x, or it doesn't change anything. So this will simply be function value. So this is the function now at p is equals to 0. So if I simply substitute pi 0 by 2, this will give me half times sine 0, which is 0. Okay. All right. Very good. Now comes the next problem. Minus infinite to plus infinite, e power minus 2t into delta 2t minus 2 dt. Yeah, if you have solved it, you can straight away tell me the answer. Okay, so 1 by e square. Okay, so I will put it as an option. Option A, 1 by e square. Any other answers? Okay, so e power minus 4 into 1 by half. So I think you are saying this. Am I correct, Sahil? Or is it something else? Yes, okay. Okay, any other answers? No? Okay, so how many of you think it is option A? How many of you think it is option B? No one, no? So not option A, not option B then. Okay, so you guess 1 by 2 into e. Okay, so e power 2 is also in the denominator, I guess. Okay, which is option C. All right. So, okay, so let's solve again, as I said, option A. Okay. Okay, so let's solve this in my way. I will again substitute some p, variable p as 2t minus 2. Now from here, dp will be 2 dt, right? And t will be p plus 2 by 2, right? So t is p plus 2 by 2, dp is 2 dt. If I substitute, the limits won't change. E power minus 2 into p plus 2 by 2, right? So minus 2 times p plus 2 into delta 2t minus 2, 2t minus 2, the whole thing will become p, and this will be dt is half dp, so half dp. Now if I pull out half out, minus infinite to plus infinite, e power, this and this will get cancelled out. We'll have e power minus p minus 2 to delta p dp. Now this is your function f of p. So this will be half f of 0. So where f of p is e power minus p minus 2. If I substitute 0 in place of p, I'll get f of 0, which is e power minus 0 minus 2, which is half times e power minus 2. Okay. So what's happening? So the right answer is option C. It is not option A, option B. Okay, so that is why I said. So this thing may look very simple, but when it comes to the problems, it is very, very difficult. Let's all one more. So till now we took the limits are from minus infinite to plus infinite. Now we will see how this limits also can affect. So if I consider this limit from minus 2 to plus 2, and I have let's say x plus 3 whole square and delta x minus 4 dx. What will this be? Anyone? So this particular problem, the one who guesses will get it right. Okay, so it's the most guessed value. And in signals and systems, with respect to Dirac delta, you can always has 50% chance that the integral will be 0. Okay, so three possible values, maybe 95%, 90%, let's say, will be between 0, 1, infinite. Okay, so now guess at least. So if you don't know how to solve, at least guess whether it will be infinite or 1 or 0. No. Am I audible? Okay. Thank God. At least I got two responses. Okay. Why is it 0? Why is it 0? Why not? This is something else. Why not this is 4 plus 3 whole square, which is 49? Huh. Because Dirac delta is outside the range is one thing. Yeah, correct. So you see this impulse. This impulse is at 4, value 4, which is outside the limit, right? So within this limits minus 2 to this is 0. So therefore, this is not correct. This whole integral will be 0. So sometimes even the limits play very crucial role. Okay. So sometimes what happens is you will get lot of confused. For this, I want at least some 10 people to answer. At least. For standalones, you should definitely answer this. Sit, solve. So I'll give you some solid 3 to 4 minutes time. And I can assure you, quiz one, the problems will be of this level. Okay. So even with the Dirac delta, it is not going to be easy. Okay. So time is 9:34. So I'll give you guys till 9:38 maybe. So try to solve this and we'll do one more problem. Okay. So which will be slightly, which I guess at least slightly difficult. And we'll end the session. And after this session, you should be able to solve problems related to Dirac delta. Okay, so I have launched one more poll in the Gmeet. So it's like if you have solved this particular problem, you just click yes or else click no. Okay, so this is for all the students who are in this session. What you have to do is click on the activities, click on the polls inside it. If you have solved this particular problem, which is on the screen, sixth problem, then click yes or else click no. Yeah, and I will close this poll by 9:40. Only 2 minutes you have. So just click on this poll as I mentioned earlier. So your attendance will be considered if only if you attend these polls, like attempt these polls. Okay, solving. Okay. Okay, okay. So those who are solving, try solving it. Okay. Once you are done, then do the polling. Okay, I think we will end today's session with this particular problem. So the last problem we'll see. So it is not, it will be slightly theoretical again, which I don't want to stress you guys. I think I have stressed you enough, I hope. So these are all thoughts I have on Dirac Delta. So it is good if you also start thinking about it and get a good understanding of Dirac Delta. Because the very next week, week 5, you will see the importance of Dirac Delta. Week 5, week 6, when we introduce LTI systems. So just with impulse response, you can actually describe everything about the system. So when we say impulse response, you should know what that means, and definitely the base is this Dirac Delta impulse signal. Okay. So yeah, those who have solved, what answers did you get? I expect at least three different answers will come from you. Yeah, any answers? Come on, fine, it's fine. Even though it is wrong or correct or it's okay. Even now you can just guess what would be the answer.
So, sir, in this, the delta will be the impulse will be at t is equals to 1 by 2, and we will put t is equals to 1 by 2 at other points because 1 by 2 is in between the range. So,
Hmm.
yeah. So
So
this will
you
be 1
say,
into 2.25 by 4.
sorry,
So
one.
the answer would be around 1 by e into 25 by 4, I guess.
Okay, so 1 by E into
25 by 4.
25 by 4. Okay. Any other answers? Any other answers? 25 by 4E, which is equivalent to what Hari said. 25 by 80. Okay. Okay, 25 by 80. All right. All right, 25 by 80. One more. Any other answers?
Oh, sorry. Here we have scaled also, so this delta will be
Okay.
one.
Okay, so 25 by 80. Is there
Yeah.
anyone? I expected one answer like this. Anybody who got this? 9e by 4.
Sir, t is equals to when we put t is equals to 1 by 2 and then
Hmm.
1 by 2 plus 2. It is how is it possible? Like we directly
Okay.
add 1 plus
Yeah, I
2.
got it. I got it. I got it. So I expected. That's what I said. I didn't say option C is correct. I was just checking. Some of you would have got this answer.
I was thinking like this in the starting when I was thinking in my mind when
Yeah,
I wrote down that I change.
yeah. Okay, fine. So if you have understood these five problems, what we did is I did by substitutions, but if you are smart enough, you would have guessed from these five things. What we are eventually doing is we are looking this delta function closely and we are seeing where the inside part will become 0, right? So this 1 minus 2t, where will this be 0? So for what value of t will this be 0? So it will be 0 for half. Okay. So you can directly substitute half here, but you should be little bit more careful, or you should be slightly careful whether there is any scaling factor that is multiplying to your time domain. Okay, so you should be careful about that. So 1 minus 2t is different from half minus t, right? So delta half minus t is different or not equal to delta 1 minus 2t. But both the signals will have impulse at half, right? And this is not equals to delta 2t minus 1. This is not equals to delta. Oh, sorry. This is equals to delta 2t minus 1. But this is not equals to delta t minus half. Okay. So if there is some scaling to your delta, then you have to divide it by that scaling factor. Okay. So that's really important. So that's the shortcut in some sense. So if you are sure that this t is falling inside your limits, so that's your first check. So check where this delta function, the input is being 0, is becoming 0. So you check that here t is equals to half. And the next step is whether t is equals to half is in your limits or not. See that. If it is not in your limits, straight away 0. If it is within your limits, then check is there any scaling factor. In our delta, there is a scaling factor. The factor is 2. So if it is 2, scaling factor is 2, then you should multiply by 1 by scaling factor, which is 1 by 2 outside. And the next is wherever your delta is becoming 0, sorry. So delta of the inside part becomes 0, half plus 2 whole square. And if you simplify this, e power minus 1 into, so half plus 2 is 5 by 2 whole square, which is 25 by 4, which will give you 25 by 8e. Okay, so this is like a 3-step process and easy process to follow. Okay, so the first thing is you just check where the delta of something inside, whatever it is, the scaled shifted time signal, the scale shifted version of the time, you equate it to 0. So that's where you will have the impulse, right? So when you equate it to 0, you'll get some value. Check whether that value is within the limits or not. If it is within the limits, you then check is there a scaling factor getting multiplied to your time domain. And you take 1 by that scaling factor times you substitute this in this function and write down the result. So that will be your answer. Okay, so this way you will never go wrong. Okay, so this is, if you follow these 3 steps which I discussed, you'll never go wrong in these kind of problems. Okay, so given a function times some scale shift version of delta, and it is being integrated from some limits, between some limits, you can get the answer easily. Is this clear? Is this okay? Any doubts? Okay, so now I think you can solve all the delta related problems in graded assignments, right? So I expect so. And also, as I said, the starting 50 minutes, I just wanted to tell you guys that the Dirac delta looks easy but not easy. So if you go by intuitions, it makes sense. Like it is very trivial. It feels like it is very trivial. But the mathematical reasoning behind the Dirac delta is very, very complicated and it's not that easy. So when we pull in mathematics into uh, uh, maybe math into here, then Dirac delta is the scariest part. Okay. So yeah. So I think whatever I wanted to discuss, I'm done. If you have any doubts, you can ask me. Or on Saturday, we will do slide demo on the MATLAB. Okay. By the way, we have released the first programming assignment in the MATLAB grader. I saw most of you have signed in, but there are still some 20 people who are yet to sign in. 20 or 18 odd people who are yet to sign in. So if you have, if you know some of your friends have registered to this course, kindly let them know that there is a programming component also in this program. So in this course, and that need to be done. Okay. All right, then if there are no doubts,